2025 edition of the Technical Advisory Council of the Confidential Computing Consortium. We are an open and collaborative group here. Everybody's welcome to join into the conversation in a constructive way. In a few slides, if you haven't been here before, you're going to be invited to introduce yourself. Sometimes it's easier to engage if everybody has been introduced. You're not obligated to, but we like to get to know one another here. We are also under the obligations of the antitrust policy of the Linux Foundation, and you can read more about that on linuxfoundation.org/antitrust-policy. Pretty jammed-packed schedule for today. We heard last time from the proposers of the DSTAC project, and I know we have some vacations going on this week for some of the voting members of the TAC. So if we do not end up with quorum in a slide, one slide from now, then we'll probably move that vote to the email list. And I know we've got Sheldon on if anybody had last minute questions, but we won't be asking him to go through the presentation again. After that, Ravi's going to update us on the world of RISC-V. And then we've got some downloads from Chris Butler, who's been working with confidential computing in the field. And I think we'll be interested to hear what kind of feedback he's gotten out there with actual customers. And then we have the annual review. Maybe it's the first annual review for Manatee, because I think we launched that project last year, didn't we? I look around as though I'll see nods on the cameras. All right, and then I think that'll probably bring things to a close. We won't be touching the glossary today. Any other agenda topics I missed? Nope. Okay, well, let's do a quick check. Just as I eyeball the list here, I'm pretty sure that we do not have quorum. So if that changes later in the meeting and somebody notices that we do reach quorum, go ahead and let me know and we can switch quickly to a vote. But otherwise, I think we will end up putting the DSTAC vote to the list. Now, for those of you who haven't had a chance to introduce yourself at least twice, you are welcome at this point to just come off of mute and let us know how you like to be addressed, where you're joining from, and what your interest in confidential computing is. I see Jeff on chat mentioning that it's unavailable to pop off of mute, but saying hi from chat. Thanks for joining, Jeff.
Hello, Al. When I talk. Oh, sorry.
Hello. Yeah, just want to say hello to everyone here. I'm Hong from Fala Network. I'm the CTO of the Fala Network company. Yeah, we have been building for a lot of a very long time. We even started using Mingshi's original T-Clave SDK before, and now we're building on TDX. Yeah, good to see everyone here.
Great, thanks for joining, Hong.
Thank you.
Hey everybody, can you see me? Mark Gentry, longtime Intel, currently Chase with Mark Novak, the Marks. And yeah, we're looking to see how Chase in general, how Chase can improve security both internal and external using confidential computing.
That's great. I'm glad to see you joining, making a team of Marks over there.
I probably can go next. I'm first time here in the call. Hey, I am Roman. Almost 20 years doing cybersecurity stuff. Now I'm at Red Hat, principal architect responsible for our security community and industry engagements. Happy to be here.
Nice to have you on here, Roman. All right, I think with that, feel free to introduce yourself as we go along if you haven't had a chance. But I don't see anybody else coming off of mute, so I'm going to just go ahead and move us along here. Last time, as I mentioned, we had the proposal that was provided by Sheldon and others at Fala Networks, and we also we checked in on the glossary, I think, in that we revisited what the motivation for it was, and we wanted to get some feedback yet from the Cloud Security Alliance who might be using it before we decide one way or another about how much we're going to invest in it. But we are essentially deferring further work on that until we have feedback from the GRC SIG or the principals involved in that particular thread. If you have not had a chance to read this blog post from one of the mentees who went through the mentorship program that we have, I was certainly surprised by the amount of work accomplished there and on some pretty interesting topics with attestation formats. So I'm going to drop the link in the chat for people. Encourage you to read that after the meeting. The other thing that's coming up on the horizon here is that Mingchen and TikTok has proposed a funding mechanism for academic work that's been proposed at the board level, and there's an initial technical scope that is part of that document. And in the next week, we'll be sharing that with the TAC list. And what we want is for you to connect with your board members and provide your feedback and understand their interest in this work. And it's one of these things where I think until we start trying to advance it with everybody, that it just kind of sits there in the background, or it has the risk of not moving forward unless we try to make some forward progress with it. Mike?
Yeah, just to say, I've been involved with some of the discussions about what this looks like at the board level, and it sounds like a great thing. We have a very good model. The EBPF Foundation has done it before, and so we know how to copy it, which is fantastic. So what we're really keen to do is to get people to talk to their companies and say, yes, we might be in a position to provide some money to this. Doesn't need to be this year; it could be the next budget year, so that we can start kind of set this up. And the other thing is, at some point, assuming it goes ahead, we're going to want some volunteers to help us be on the sort of project board to decide what gets funding and stuff. So this is it's a really great idea. I'd love to see it happen. But we do need support. Sort of at senior levels. So please, as you say, Dan, get sync with your board rep. Thanks.
Yeah, thanks. And let me just maybe reword what I was trying to get across before, which is sometimes when these proposals come out, the board members look at it and think, well, I didn't hear anything from my TAC member, so I don't know if I care about it. And then when we talk about things in the TAC, sometimes TAC members think, I never heard anything from my board member, so I don't know if this is going to be funded anyway. So let's not have that problem. Please just go ahead and proactively engage with the other constituencies within your company, at least your board member, if not others within it, and then we can move this forward. Okay, so the next thing that I had on the list was the vote, but I think we are still quite a bit short of quorum for a vote. And I don't think that's changed. So I will just go ahead and move us right along into the Risk 5 update from Ravi Sahita. Ravi's joining us to talk about the latest and greatest there. So I will stop sharing. Turn things over to Ravi.
Thanks, Dan. Screens. it's visible.
Yeah, I can see it.
All right, cool. And just time check. Do I have about 15 minutes, 30 minutes? We have a lot of things on the agenda, so I wanted to.
Yeah,
sure
so
I stay.
we about 30 minutes all in, including Q&A.
Okay, so I'll have to go a bit faster. I might have too much material, but people can look at it offline as
great.
well. Yeah. So my name is Ravi Sahita. This is a sort of a short update on RISC-V confidential computing or confidential VM extension, also called COVE as a short form. This is work that's been going on for about a year and a half now in the RISC-V task groups that work on it. There's two task groups that work on it. I also vice chair the RISC-V security horizontal committee in RISC-V, which basically works on various security topics. Confidential computing being one of them, but the other key topics are sort of microarchitectural side channel mitigation or ISA related to that. Control flow integrity features for the RISC-V ISA. There's been some discussion recently going on memory tagging. We also were working on publishing a broader security model for RISC-V, which is in a sort of a more decent draft shape right now. Probably going to get ratified this year. These specs on the confidential computing side is sort of split into ISA and non-ISA parts, and I'll try to touch upon both today to give an update. So I don't need to give any introduction to this forum, which is the best part. Like everybody here is familiar with confidential computing, so I don't have any material describing confidential computing here. Just some of the key attributes we want to achieve for trusted execution environments that want to support confidential computing use cases. And as I said, the work is split in RISC-V to make it sort of more modular into a security model spec, which is basically largely a non-normative spec that describes threat models and different building blocks available in RISC-V, not just for confidential computing, for various different use cases, and also provide some recommendations. I won't touch upon that one. People can go look that up on the RISC-V. There is a specific task group that works on the security model. I'll touch a little bit on where we are at with the ISA extensions for RISC-V, specifically describe a little bit on what we call RISC-V supervisor domains, ISA extension. As you know, RISC-V works on a lot of these like smaller modular ISA extensions to make them more accessible for different use cases, different implementations, whether it's embedded or data center. Our focus, obviously, from a confidential computing perspective, has been on the data center side of things, but the supervisor domain ISA is built in a way where it can support, different types of use cases, and it's not very specific to confidential computing per se. So it's sort of more on the here's an isolation primitive, and we will see how we can apply it for confidential computing. There's also non-ISA stuff that we need to obviously worry about from a confidential computing perspective. And RISC-V terminology for non-ISA can be hardware or software. It's just that something that's not ISA corresponding to the RISC-V CPU spec, right, or the priv ISA spec. And so, yeah, we sort of have this work kind of split between, there's the SOC infrastructure working group in RISC-V that works on some non-ISA hardware parts, like things like IOMMU and extensions. So the IOMMU spec was recently ratified, or last year ratified from in RISC-V. There was also an advanced interrupt architecture spec that was ratified the year before, which are both ratified stable specs, and we build on some of those primitives, right? And finally, but not the least, is an important ABI spec, right, for COVE, which is also categorized as a non-ISA software spec. And this is a separate TG under the security HC. The name is a bit confusing. Just historically, it was called Application Processor TE or AppTE, because again, it was sort of targeted as a general specification. But the main application of that is the confidential computing, supporting confidential computing workloads rather. So that's the Cove, our confidential VM extension in RISC-V. And that ABI also has two sort of branches of it. There's a baseline ABI spec, and then there is a Cove IO ABI spec, which touches more on the TE-IO interactions. Most implementations sort of have this like two-pronged approach to address confidential computing. We also have done it that way in RISC-V, but the specs are sort of going through the ratification process almost in parallel, right? So the revision numbers, etc., are different. So just FYI. Yeah, go ahead, Mike.
Mike, you are on mute.
Muted.
Oh, sorry. Yeah. How do you achieve isolation? Is it done via encryption or another isolation mechanism, memory mechanism?
Yeah, so I'll touch upon that in the supervisor domains. ISA, a quick TLDR is this supervisor domains is largely a MMU or a memory isolation, physical memory isolation primitive. Memory encryption and things like that are sort of platform implementation specific for RISC-V because they don't really concern the heart per se, but the heart through the supervisor domain ISA provides context identifiers, which can be used downstream for doing memory encryption. So I'll touch upon that a little bit. Yeah. So the supervisor domains ISA, as I mentioned, sort of builds on the Priv ISA. It's a Priv ISA extension in RISC-V. And if people are familiar with the RISC-V specs, there's a Priv ISA specification documentation and a non-Priv or user mode Priv ISA documentation. So this is largely a Priv ISA extension. And this is just a 50,000 foot view into the RISC-V privilege level. So, people are familiar, mostly familiar with this, I'm sure. Basically, RISC-V has user mode, supervisor mode, and machine mode, which basically give you execution context at different privilege levels. And what supervisor domain essentially adds is the notion of through the TCB of the machine mode, which is here called as a root domain security manager. You can essentially create separate supervisor execution contexts, right? And the memory isolation between that is essentially achieved through either legacy mechanisms in RISC-V, which are physical memory protection, which are very static and coarse grained. So those are okay for certain embedded class platforms, and they have been used in implementations like Keystone and others in the past. But those are limited when it comes to interacting with the rich OS environments, right, which do memory management at page granularities at different architectural sizes. So the MPT or memory protection table is an isolation capability added to supervisor domains to essentially allow different supervisor domains to be active. And I'm showing two here just as an example. The architecture obviously can support more than two depending on use cases, but you can think of creating either very simple models like a secure and a non-secure domain, or you can create a host and a confidential domain, or multiple confidential domains for that matter. And they're managed under the purview of this the M mode root domain manager, right? Just for simplicity, also I'm only showing the S and U mode supported in the supervisor domains here. You can also support the hypervisor extension in any of the supervisor domains, which is also a ratified spec in RISC-V through which hardware virtual machines in RISC-V are supported. When hypervisor, I don't know if I have a slide picture on that or not, but when the hypervisor extension is enabled, you essentially get a VU and a VS modes in addition to the UNS mode, right? Essentially by activating a V bit on the heart, which is basically a terminology for the RISC-V hardware thread. And then within the advantage of sort of this supervisor domains approach is you're not restricted to obviously one single alternate supervisor domain. You can create multiple depending on your threat model and use case. And then it also leverages a large part of the existing Priv ISA to essentially further isolate within workloads within that within a supervisor domain context. So for example, as shown here in the SDID2, you can basically have an OS environment that's partitioning things using SV. SV is the extension name in RISC-V for the virtual management, with the virtual memory management architecture. So that's basically in other architectures, the first level page tables. If the hypervisor extension is active as well in a particular supervisor domain, then it can create guest contexts that are supported through the guest level G stage paging tables, right? So it basically lets us use a lot of the previsor and not have to sort of renegotiate the ISA contracts for that, and cleanly provides us a context that can be tagged in internal caches and things like that, right? So you have the ACID at the process level, or the address space identifier, which acts as a tag at the process address level. You have a VM ID, which is not shown here. I think I have another picture, which is if you have the hypervisor extension enabled, which tags things that are controlled by the hypervisor that's active within the supervisor domain. And then finally, you have the SDID, which is a supervisor domain identifier that lets you tag things in addition as in the context of a supervisor domain, right? So once you've isolated memory through the empty structures, if they're active, you basically perform your page walks as normal to the first level and G state page tables, but every physical memory access also checks the memory protection tables to enforce the isolation between the supervisor domains, right? And then different implementations can obviously support those implementations with appropriate caching structures and things like that to address performance, right? Just like traditional, page table structures have done. Let me see if I might have a hypervisor extension figure later on. But that's sort of the general idea behind supervisor domains. And the spec, in addition to covering the MPT ISA, also covers the baseline ISA to create supervisor domain identifiers, configure them, and a bunch of other sub-extensions that cover things like how to secure interrupts in the context of supervisor domains, how to interact with the IO, MMU, etc. Right? And you'll see that all sort of clubbed together in the supervisor domain spec. And it's actually not a large spec. It's actually pretty compact. Yeah, go ahead, Dan.
Could you say a little bit more about the hypervisor in this context? I think a lot of us are used to thinking of the hypervisor from the host hypervisor perspective with some of the other technologies, that's an untrusted component. But we also have some work with Coconut, for example, where you've got sort of nested virtualization. And it's not actually nested virtualization, but something to that effect.
Right. Yeah, so yeah, maybe in hindsight, I should have put the hypervisor picture, but actually, if I go to the Cove slide, and if I jump there for a second, you'll be able to see how it's applied to Cove. So this is basically like a two supervisor domain model, right? Showing the hypervisor active on the host side, right? So what happens with the host, assume that this second supervisor domain doesn't exist, right? Your OS typically comes up through your secure boot process, whatever M-mode firmware is run on the platform to initialize platform capabilities. You pass on control to the host OS. The host OS starts running in S mode. At some point, it can activate the hypervisor extension, effectively like a type 2 hypervisor, right? Effectively like Linux KVM. So think of Linux KVM running in your host supervisor domain. At any point, based on how the platform was bootstrapped, this hosting domain can effectively activate a secondary supervisor domain, right? And this supervisor domain, sort of depending on how it's configured, is able to run effectively a hypervisor component or a HS mode component, right? It doesn't have to be a fully blown hypervisor. So as shown in this picture here, it uses the ISA available to the S mode and the HS mode, right? For RISC-V, but it can essentially be like a restrictive software module, which in the confidential computing industry has generically been called the TSM, right? So you have a TSM that's running in HS mode in your in one of the alternate supervisor domains that can effectively act as the gatekeeper for any confidential VM extensions that you want to manage, right? Or context that you want to manage, right? So it's a very, I think it's a well understood canonical model where your host OS can run legacy or non-confidential VMs, just like it normally does with the ISA as it works right now. And through the Cove ABI, you interact with the TSM, right? Which basically runs in the HS mode and can manage partitioned Cove guest VMs, right? Or TVMs, right? And that's really why we have the Cove ABI, is to basically interact with the RISC-V architecture specific portions, right? Whereas a lot of the Linux KVM interactions can dovetail into like some of the standard flows that we have for confidential VM management, right? So that's how it's sort of like, combined into the architecture.
Yeah,
So hopefully
yeah, I
this
think seeing it as the TSM makes it clear to me anyway what that role was. Thank you.
Yeah. And as the architecture describes, you could have essentially another alternate confidential domain as well, right? And the host can decide what resources are given to which confidential domain, and the TSM manages the assets within that confidential domain, right? Or partitions assets within that domain. So this is, I knew I didn't have too much time today, so I sort of going through the gory details of the MPT extension. I sort of just showed like the logical view of it, right? Where it actually enforces checks. So as I said, RISC-V, sort of the legacy privilege architecture, already had a PMP check, which is basically a physical memory protection for like low-level firmware isolation, and that applies as it does right now. But with SMMPT active, you essentially get this additional memory protection table lookup that happens at the tail end of these nested walks, right? If a nested walk is active, if only a VS stage is active or a G stage is active, that works too, right? So it doesn't restrict the modes that are active in a particular supervisor domain. It basically enforces the RDSM's property of isolating memory, right? And SMMPT supports various different modes, so it can compose well with the SV architecture from RISC-V. So you can essentially create like you have a SMMPT for RISC-V 32 or various SMMPT modes for RISC-V 64, right? Depending on the architecture you're using, and even within RISC-V 64, depending on the physical address width you're supporting, you can support different SMMPT modes. So that they compose again well with your the physical address width on your platform, right? And that leads to efficiencies in terms of like how we perform the SMMPT lookup. And the same, we want to basically follow the same kind of model from the IO side, because we want this model to be, this architecture to be ready for sort of the TEIO requirements from the get-go. And that's really addressed through the IO side of the extensions, or the non-ISA extensions that I mentioned, where the IOMMU that's defined in RISC-V already addresses like a device context lookup based on a device ID to essentially walk through take the IOVA through its translation to reach the system physical address from the IO DMA perspective. The MPT essentially, through an IOMPT extension, allows to look up a particular IOMMU domain and then a particular MPT structure attached to that IOMMU domain, so that you can perform the right lookup even from a DMA perspective, right? And it takes into account things like which IOMMU domain you use is identified at runtime, even if that VM is not scheduled on the platform, and things like that, right? But this essentially gives us like a base primitive, right, that we can use, for confidential computing, but also for other use cases where people may say, hey, I'm not really trying to build confidential computing, but I want a basic isolation model for multi-tenant platforms. I have like an embedded platform where I have RV32, and I want a really lightweight MPT implementation, which works well with the rich OS environment, but is not trying to do all the additional things needed for confidential computing, right? So it really gives us a very, small and well-defined primitive, and then it gets used in the context of confidential computing with other platform capabilities. So speaking of other platform capabilities, and I apologize, this is a bit low level, but this is a slide that I had, which I thought people would probably appreciate here. But the general idea is essentially to say, when you have supervisor domains active, and we leverage the advanced interrupt architecture spec in RISC-V already, which has the ability to work nicely with things like the hypervisor extension, where essentially, in addition to the base AI, where you have like a M mode interrupt file to deliver message signal interrupts, or a S mode interrupt file to deliver S mode level interrupts to a supervisor context, you also have guest interrupt files, right? If you have the hypervisor extension implemented. So what the SMSDIA, or which is supervisor domain interrupt assignment, part of the spec lets you do is essentially assign either well-defined supervisor interrupt domain context, which is basically a a grouping of at least one supervisor interrupt file and optionally a number of guest interrupt files based on configuration to a supervisor domain, right? So you can essentially, again, reuse the same contract that AIA has defined from a hard side to access registers to interrogate, like, is a supervisor interrupt pending? Can I enable or disable supervisor interrupts? Do I want to delegate any supervisor interrupts? That same interface gets used within the context of the supervisor domain. But this lets the RDSM essentially carve out the assignment of those supervisor domain interrupt files to appropriate supervisor domains, right? So that's really what this sort of muxing is showing here, that the M mode controlling software or the RDSM can configure, like, hey, I want to group these interrupt files in this way and assign it to this particular supervisor domain. And it effectively activates that through these through a configuration CSR that's provided for a particular supervisor domain. And then since this is the RDSM is sort of the controlling authority, there's a new MSDEIP or an external interrupt pending signal added that's managed by that RDSM that tells it that, hey, an external interrupt is pending for a supervisor domain, right? So it can appropriately do context switching if needed, right? And the architecture is built in such a way that if that particular supervisor domain context is already active on a particular heart, then that interrupt, once enabled by that supervisor context and the RDSM, can effectively be directly delivered to that supervisor domain context, right? So it gives us all the performance benefits of the RDSM not having to emulate the entire AIA architecture, which it can do. It can sort of like emulate the AIA CSRs and sort of manage this manually, but this gives us a more performant way to do it. There's also another sub-extension defined as part of SMSDIA, which is again meant for like lightweight embedded applications, where somebody might say, hey, I'm not building fully blown multiple supervisor interrupt domains. I'm just taking my existing implementation of AIA, which has one supervisor context and a bunch of guest interrupt files, and I'm only going to give certain guest interrupt files to a particular supervisor domain, right? So think of that as like a sort of a lighter weight assignment or delegation of guest interrupt files. And that's possible via the sub extension called out in the bottom called SMGEIN, which basically is a simpler implementation. All it requires is a CSR showing a bitmap, right? Of like, hey, within a particular AI implementation, these guest interrupt files are assigned to a particular domain that's identified on a particular heart, right? So it sort of gives you a primitive again, which sort of covers the entire range of like very simple embedded applications to much more advanced data center applications to do direct assignment, right? Under the control of the TCB. And then this is sort of a third important primitive, right, which allows for the IO side of the interactions, right? Like I said, we want to make sure like the core interfaces and the primitives are sort of compatible with the TEIO architecture that PCIe and other standards bodies are building in terms of using SPDM for device authentication, and then more importantly using TDIS for integrating device interface state as it's assigned to confidential VMs. So for that, on the non-ISA side on RISC-V platforms, we need a way to essentially say these devices under these IOMMU domains are assigned to a particular supervisor domain context, right? And that's really what IOMPD does. So what this picture is showing is really we use the IOMMU spec in RISC-V as is, right? There's no changes to the IOMMU spec. You could have one or more IOMMU implementations on the platform connected to an IO bridge. And the IOMPT effectively adds this gray block in the bottom, right? It has basically two parts. It's got a supervisor domain classifier, which is basically a rule interface that says, hey, if you get a device request of this type, let's say PCIe with this, this requester ID or this range of requester IDs, map it to this corresponding SDID, right? So it corresponds to this supervisor domain instance, right? And then once you've sort of, once the IO bridge has fetched that information based on an inbound request, it can then, once it knows the IOMMU domain, it can interact with the IOMMU domain to essentially perform nested MPT walks, right? So the IOMMU walk happens as normal, as I described in that logical flow earlier. But as you're translating the IOVA to the SPA, you would also look up the MPT checks to perform the access control checks required for that physical memory that's being accessed. And finally, similarly, the PMA checks, which is the physical memory attribute checks that are performed, you effectively get an SPA inbound, right, which has converted that IOVA into an SPA, and it knows exactly which which MPT to enforce for it. The IOMP data structures, MPT data structures all stay in memory as normal, as defined by the main spec, by the SMMPT spec and the IOMP spec. And then you essentially have a translated physically access controlled memory access coming in, right? And again, the same downstream checks can apply. If you're taking the SDID and translating it to an encryption context, you would do that normally as part of your memory controller, right? So whether you're accessing cache or whether you're accessing memory controller, the same access control can apply in the cache or in memory, right? So this construct is really letting people again decide the complexity of their implementations. You can have like a single IOMMU domain and a very simple MPT checker, because MPT checker defines essentially an interface to a set of CSRs that give you like a programming interface, which is based on MMIO. And the MPT check and all those parts remain exactly the same as the main spec defines, right?
Maybe Ravi,
yeah.
to Mike's, or I'm sorry, I raised my hand. To Mike's earlier question, sort of where would encryption, just to sort of level set here, where would encryption be? And this comprehends encryption, right?
Yeah. So the memory controller typically contains the encryption, right? And you drive that based on context that based on the request, right, coming from the heart. So if the heart is in one of the supervisor domain contexts that has been identified as a confidential domain, you would essentially have an SDID that you could drive on accesses from the confidential domain. In addition, you might have other context information that you have on the local bus, but that's largely what you would use to essentially make a choice of what encryption context to use on the memory controller, right?
Great, thanks.
But did you also say that encryption is sort of a vendor decision, that your isolation is more guaranteed from the physical access request?
So that's right. The supervisor domain spec doesn't describe an encryption model, but if you look at the Cove spec, where we have a threat model specific to confidential computing, there obviously we basically say you must support encryption for memory, right? But that implementation of how the memory encryption is implemented and what modes are implemented on the memory controller is an implementation decision, right? So we have some recommendations on how somebody can take the SDID context and map it to an encryption domain, but we don't require it as part of the supervisor domain spec, because again, that's a risk-ism, right? Like they don't want to like conflate sort of requirements of one use case on the primitives in the ISA spec. So the ISA spec is sort of very at a very basic primitive level, right? It gives you, like, for example, SMMPT. Basically, if you look at the way the spec is implemented, you could literally just implement SMSDID, which is the SDID part, and MPT, and not implement anything else, right? Unless you needed to. If you're doing TEIO, you would say, oh yeah, I'm going to implement SMSDIA and IOMPT in addition, right? Mm-hmm. And then there are other extensions like for CVQRI, which is basically a QoS register interface. So you can do like memory bandwidth and cache allocation assignment enforcement. And again, if you some implementations may not implement that, right? So there are a set of primitives you will choose, but the Cove spec, which has a more threat model that's focused on confidential computing, sort of pulls all this together to say you shall implement, all of these requirements, right? So that brings us to the software, which really brings all of this stuff together, right? So you have, let's say you have an implementation that chose to implement supervisor domains. You probably have a root of trust on the platform to do your initial bootstrap or, handle dynamic updates, things like that. You probably have an IOMMU and IOMPT implementation on the platform. So basically, Cove gives you an API, which essentially has two interfaces, right? It has a Cove H interface, which is a host-facing interface, and a Cove G interface, which is a guest-facing interface, right? I mean, if people are familiar with a lot of these flows, whether it's on other architectures like AMD, Intel, TDX, or even ARM CCA, a lot of these interfaces and interactions sort of dovetail nicely into some of the Linux AVM interfaces being built for the host for those other architectures, right? So we're not trying to do something completely different here, right? It's just we have to map some of these actions and verbs on the interface side from the host to the RISC-V architecture specific primitives that we just described, right? So that's essentially what the Cove ABI lets us achieve through these implementations that sit in the TSM or in the TSM driver that's shown in the M mode, right? So the TSM driver functions are sort of they basically extend the root of trust from the ROT, right? And they support attestation. They support some of the basic context switching between supervisor domains, things like that. And the TSM essentially really owns the implementation of the Cove ABI, right? So it supports the host-facing interface that's mediated through the RDSM or the TSM driver, and the Cove guest interface that it provides to the guest contexts, right? And like I said, there's sort of a companion spec that addresses Cove IO. So this is when you have a PCIe device or any other device, accelerator interface, things like that you want to assign to a confidential VM. Again, there is a bunch of discussions on the Linux mailing lists on what are the common set of verbs we need to support for, discovering a device, authenticating a device, connecting a device, and binding a device to the confidential VM. So we're trying to make sure like the Cove ABI for IO sort of dovetails again well into that spec. But we have to again manage some of these like platform side interactions with the IOMMU, with the IOMPT through that under the context of those APIs, right? So there's a link at the bottom for people who are interested. But this flow again should be, I think, well understood to people here on how the device is first authenticated, and then you might have either the entire device or a virtual function on the device that's assigned to a TVM. When the TVM comes up, it essentially verifies the device state interface through TDISP and then accepts the interface, right, which essentially binds it at that point for use by the TVM, right? And again, the use case is very similar. We want to avoid any additional performance overheads for assigning device interfaces into TVMs. So once your device is bound, you're essentially going through a fast data path with the translations being performed through the IOMMU and then address translations being cached as required. This is sort of a bird's eye view of the different Cove ABIs that are defined in the spec as it stands right now. The spec has largely been pretty stable. We are probably going to rev the spec in the next couple of months. We're just waiting to finalize the ISA specs right now. They're basically completed what we call an architecture review in the TG or rather in the HC. So once that supervisor domain spec is sort of ratified, we'll probably circle back and finish the ratification of the Cove spec. But yeah, this is just for background for people to look at later on. So currently where we are at is, like I said, we are ratifying the specs for the ISA, and to do that, we basically have a bunch of emulation sort of projects going on. So one is to use QEMU to essentially emulate the ISA specs, right? So these are taking the core parts of the ISA specs and implementing it in QEMU. So this is a work in progress. We have sort of an older version of the spec implemented right now, and that's being revised to the current version of the 0.41 spec. So this will allow us to basically have a emulation platform until we get full hardware. There are hardware implementations of the hypervisor extension available right now from Sci5 and other folks. So people have been using that as well to build some implementations. But we wanted to start adding some of the supervisor domain implementations into QEMU as well. The one other sort of related thing to the emulation framework is tests that allow different use cases to use that emulation framework, right? So we are basically using Linux and KVM unit tests to essentially bootstrap this capability. So you can essentially bring up the emulation framework, bring up more than one supervisor domain running standard Linux with device tree, and then you can do perform some smoke tests with it to make sure like, oh, your MPT access properties are working correctly. You can invalidate permissions, etc. Right? So this lets any use case sort of like validate that their emulation platform is up to spec, right? And there's different deployment models for Cove that are described in the Cove spec, and this test will sort of suffice for any and all of these use cases. So that's sort of the goal behind creating this support framework. And then once we have that sort of infrastructure in place, anybody can take the Cove implementations and put it on that framework, right? So currently we have a TSM implementation that's being revised right now that's based on Rust called Salus. And then, once we have updated the QEMU emulated platform, we can start using Salus with that updated spec, right? To test out some of the Cove interfaces, right? There's also some coordination going on with PKVM for like an embedded platform in the RISE community, which is a software work group for RISC-V. Attestation side of things, again, I don't need to give this background to people here. I think we've talked about this before in the attestation work group. Not many changes in this spec. We're still using the EAT format, as CWT or CBOR web tokens, and the attestation certificate or attestation flow is standard TCG dice based identities that allow the TSM to essentially support TVMs with getting the entire sort of trust chain down to the hardware root of trust. And obviously, hardware root of trust is up to implementations. For our case, we've been actively using OpenTitan as the hardware root of trust, and a lot of our work has been contributing to that OpenTitan ROT to bring it sort of as an integrated root of trust into the SoC. So that's where a lot of our contributions have gone into the OpenTitan project. But that supports all of these sort of well-known standard interfaces.
So I'm sorry.
Yeah,
Robbie,
go ahead.
One like TDX and SCV, they sort of work a little bit here with TDX has RTMRs, and I think maybe it's a little bit of a stretch of an analogy, but SCV has VMPLs. So is that I guess two questions: is that level of specificity part of what we're in scope of like the common architecture spec? And then number two, what are the implementations more like SCV or more like TDX?
So we do plan to support a guest extending measurements or adding dynamic measurements. So that's the ABIs that you can see, or the SBI, extend measurements. So that will give you sort of the equivalent of like the RTMRs in TDX.
How many? That's the question, right? Or is that not?
I don't think we have a sort of a capability reporting structure in the spec, so you can actually like expand. It's not limited to 4 or anything like that. It's up to an implementation to support more, because those are really fungible resources, right? There's no hardware backing it. It's really managed by the TSM. What was your second question?
Do you have a
VMPL
construct?
Sounds like, I guess to be fair, I guess TDX sort of has both, right? TDX has the partitioning and the RTMR. So,
right.
But do you have the VM? I guess on that note, do you have the VM? Maybe AMD is a little more clean architecture. Do you have a VMPL equivalent? And that's not directly related to attestation, but it has a role.
Right. Yeah, for like service VMs and things like that. There's a couple of different ways we can. So RISC-V hypervisor extension is fully nestable or virtualizable. So you can by from the get-go support any nesting within a supervisor domain context, or even within a confidential VM context to get to begin with. But that's obviously like a bunch of like software interactions, right? The RISC-V also has in the SV definition the ability from the beginning to support like 4 VMPLs within a context, within a guest context. So I think we can support both. The TG has discussed these options, but obviously we didn't do much work on nesting because hypervisor extension was built to support nesting from the beginning. And that's already been tested. There's a KVM nesting implementation tested on the RISC-V hypervisor extension already. And in fact, there is a nested acceleration spec in RISC-V called NACL, not to be confused with the browser NACL spec, that allows for like additional optimizations of that nesting spec in RISC-V. So that all those sort of improvements can be used in the TVM context as well. So yeah, net answer is both the options are available depending on what a use case needs.
I see. Great. Thanks.
Yeah. Go ahead, Mike.
Yeah, a couple of very different questions. So the first one is what organizations are involved? I mean, Revos, obviously, but who, in terms of the work here, is it entirely in the Revos organization, or are there other folks involved? And I don't know enough about Revos to be able to understand what that means. Is my first question. Maybe let you answer that.
Yeah. So the work is being done in the context of the two organizations, really, RISC-V, where there is a bunch of RISC-V members involved in the spec development, right? So these are specifically folks, obviously, like we are involved, but there's also folks like Ventana and IBM, as well as Google, involved in the development of the specs, and Sci-Fi. Sci-Fi is sort of leading the TG for supervisor domains along with us. So there's about 4 or 5 parties involved there. The software work is being discussed both in the RISC-V TG, but now more centrally in the RISE working group. Right. So RISE is a software ecosystem sort of consortium for RISC-V, right, which has a bunch of partners, including Google, Qualcomm, and others. That's where we're talking a lot about how these POC work streams should be structured, right? But I would say, in the end, these 5 or 6 parties that I mentioned, there's sort of an overlap between their involvement in RVI and in RISE, right? There might be like one or two who are not members of RISE, but they're involved in RVI, and the discussions really, they're both under the construct of Linux Foundation. So, there's really no firewall in terms of the discussions. Yeah.
Thank you.
Yeah.
And my second question was the $1 billion one, or possibly multi-billion dollar, which is, when do you think that there's a realistic chance of having hardware and software which supports this, that you can actually do things with?
Yeah, I mean, I can't describe the timelines for Revos, but like I said, the hardware implementations for the hypervisor extensions are already available. Like, you can actually go use a Sci-Fi board with a H extension. I think it was a 0.83 version of the spec, so you had to use like some OpenSBI support to bring it up to 1.0. But you can actually like do hypervisor extension stuff now on hardware. So you can sort of kind of like expect the hardware support with supervisor domains to show up pretty soon after that. There also has been some discussion from Alibaba. Actually, Alibaba is the other party I wanted to mention on the POC side of things. They are involved both in RISE and in RISC-V, and they've expressed some plans to implement some of the supervisor domains in their implementations as well. So yeah, there are multiple folks working on it.
I'll look for hardware next week. Sounds like.
So yeah, I mean, hopefully soon. Yeah, hopefully soon.
Okay, cool. Good.
We still want to get some of these like QEMU platforms up and running, because that helps with not just the current hardware generation, but it also provides a baseline platform for other extensions people will want to build in the future, and it eases the development and ratification of other extensions. So this QEMU work will probably happen in the next couple of months as we close out the ratification of the specs, right? So yeah, so in terms of the ISA specs, we are in good shape, where the TG is happy with the ISA definition. The ARC, which is the architecture review committee in RISC-V, is happy with the definition as it stands. So we'll get that stabilized and ratified, and that'll open up the avenue for other hardware implementations, right? Because hardware implementations want to ideally implement stable ratified specs.
Of course.
Yeah.
Thank you. That's really helpful.
Yeah, sure. Yeah, this was my last slide, actually. I talked about some of the existing efforts on QEMU. There's also like a golden model in RISC-V called that's based on Spike and Sail that we'll implement for supervisor domains as we complete the ratification. There's two work streams, one on the TSM for the data center use case, and one on PKVM happening in RISE. And there's a couple of related projects that we touched, like OpenSBI, and some of the KVM tests. And there's some items that are sort of happening in the background on the Linux TE/IO interface discussions on the COCO mailing list, and then some other things that we need to update in the Cove spec, like adding dynamic updates, things like Yeah, that's what I had as an update. Hopefully that's helpful.
That was great, Robbie. I only have about 30 more minutes of questions for you.
Sure.
But I will remain silent here in case anybody else who hasn't had a chance to ask a question. We can handle another 1 minute here, and then we'll need to switch topics.
I have a quick question here. The address space that is managed for isolation, right? Is it dynamic or is it static? I believe it is dynamic. It can be changed dynamically.
Yes. Yeah,
Okay.
that was sort of one of the main goals behind MPT, is to allow architectural page sizes and allow that sort of dynamic partitioning.
Okay, thank you.
And I have one last comment, which is that it's really great work. Are there ways in which the Confidential Computing Consortium can help? Because that's partly what we're here for, and providing things like the attestation SIG and the Linux kernel SIG are ways we can do that. But if there's other things we can do, please think about that. Get in touch, and we'd love to hear about it.
Sounds good. Yeah, sounds good. I mean, definitely attestation work group we are very engaged with, and they've been really great to like bounce off ideas and get feedback from them. In fact, a lot of our attestation formats are influenced and reviewed by them. So that's been already very useful. As we build out some of the emulation platforms, I'll sort of connect back with people on like how we can, get more usage of that or get more feedback based on those.
Perfect. Thank you.
All right. Well, thanks again, Robbie. It's great to get an update. All right. And then our next
And
speaker,
I guess the
Dave.
slides will be available, right? So the just by conviction slides are available that get presented.
Yeah.
I'll
So,
send it up.
yep. That's a good reminder, though, for anybody in the community that open source organization. So everything that we do is transparent. So if you do present, we do post the slides with the minutes for the meeting, and that's in our governance repository. Now on to our next speaker. So Chris Butler again is joining us from Red Hat, where he's been working with the technology out in the field, and it sounds like a really interesting set of learnings that he's got here. So I will let Chris introduce himself further and hand things over.
Thanks, Dan. Can everyone hear me okay?
Yeah.
Yep.
Perfect. Great. At some stage, I will time out. It is quite late here, but I do appreciate the opportunity. So I'm based in Melbourne, so I'm in the Red Hat Field CTO team in APAC. So that's been really fun because we get to talk about technologies which are not quite in prime time, look for early adopters who are willing to take some risk, do some partnership with us. A lot of the focus has been on the public sector, but also telecommunications providers and banking as regulated industries where we're starting to see some generation in terms of what we do. So I've been, talking about this probably for the last year. We've been starting to experiment with this. We've got clients who are in various stages of experimentation. Some of them are coming to us to read. Some of them are coming to us to read, to understand what we're doing. Who have spent a lot more time reading the standards, the understanding what some of the chip vendors are doing today, some of whom we're educating from scratch. One of the things I will kind of start off with this, I think Mike and I had a conversation with this about a month back, which kind of generated this conversation is confidential containers as the form factor for delivering confidential computing has been the anchor for the work that we're doing. And the primary reason for that is commercial. And I don't mean that in terms of technology, but it's probably the one where we've got the richest experience, and you can play one of the larger roles in terms of what the technology is. So that's been where a lot of the conversations are. It's not saying that that's necessarily be all and end of the technology, but it's just where if you're wondering why, it's just because of where we are in the product life cycle. So I kind of wanted to talk about some of the drivers which have been starting some of these conversations. The obvious one is avoiding compliance or mitigating compliance controls. I think that's been something which has been cutting across. Encryption is my friend. Encryption means I can do things where otherwise I couldn't, because you just kind of throw that at the regulators until they run away. The more interesting ones, which have been kind of driving some of the discussions a little bit further along, is end of life, particularly cryptographic appliances, has been driving people to say, why am I doing these with boutique appliances which I can't maintain in the future, which cause me a lot of pain, when I can use an open architecture which is closer to the architecture which I use within the rest of the organization to drive security. So using CVMs or confidential containers as a mechanism to provide the security rather than having to put it onto a boutique hardware appliance. The other two, which are a bit more interesting, is I think size, weight, and power, particularly at the edge, or really in a lot of environments where people don't have capacity, particularly if they have multiple environments, is driving some interesting conversations. And capital constraints, particularly with the public sector clients, it's becoming increasingly unrealistic, which they can completely duplicate environments across multiple security levels. So I'm going to spend some time talking about some of the scenarios that I've been and one case study in terms of what we've actually got to production. So good news is we have a client who is using confidential computing in production in a core banking application. So I want to talk through the experiences and the lessons learned engaging with a client as they do this. But feel free to stop me for any questions. I can't see the chat anymore, so if there's any questions, just shout out or raise a hand. Okay, so what I wanted to kind of go through is to talk through, these are the 4 kinds of use cases which I really wanted to talk through in terms of the topologies we're seeing people use or be interested in confidential computing. Multi-level security is one. Compartmented data is a really clear one that we see. These two have been the ones which have been actually probably generating the most interest for us today. The high value asset compromise of protecting the crown jewels has been where we've seen some really strong interest. The other one, which is this physical asset compromise, which I'll talk a little bit about, is interesting because it might not be a confidential computing discussion, but it's definitely a measured computing discussion. So we might not end up having TEs, but how do we make sure that we protect data when we have an asset which might actually go walkabout? So just to kind of dive into this in a little bit more detail, one of the use cases that we've seen, particularly when we have accelerators involved, is there's no question that accelerators are in demand and driving a lot of costs. Using that, the cost and also the power consumption means that duplication is a problem. When we've got multiple security environments, that could be a government high and low side with diodes in between. It could just be a bank who are concerned about their core processing systems. People are generally wanting to keep this area as tight as possible. And the fundamental thing I would say is, for most of these clients, isolating the traffic down and using confidential compute to move traffic across zones entirely and to eliminate the zones might not be where they're at right now. But they might be looking at boutique use cases, particularly any kind of batch processing. So in the AI context, it might be something like a fine-tuning activity which they want to do. They've put just enough systems in place for inference, but they might have a larger compute capacity at a lower security zone. So think about, could I use my university HPC facility to go and train to go and do some model fine-tuning on some sensitive data? That might not even be a government workload. It's pretty easy to kind of, as soon as you say high side, to think about national security kind of use cases. It could just be, I want to be able to use that to push healthcare data down onto the larger platforms. So we kind of view this as, I want to be able to access. It's much like the cloud burst use case, but we're finding it's just as common in an on-premise use case, where people really want to do those multi-level security implementations. Being able to articulate what high trust is and their remote attestation. I'll probably come back to this. I think that the single largest challenge that I've had so far is trying to explain remote attestation as a security technology and get people's heads around this. In a cloud bursting style use case version of this, if we imagine that low side was on the public cloud, people instantly understand that high trust zone has to be something which they own on their own premises. But try explaining that to a bank and saying, how do I create a system which certain people are trusted it seems to be a little bit more of a challenging concept for people to get around. You would have thought that access, having system owners and access management was something which is relatively easy, but it seems to still be a challenge for some organizations.
So
The
before
other,
you
Yeah.
move off of
yeah,
that,
please.
so I guess from your depiction in the low side, I would
Yeah.
understand those to be confidential VMs.
Yeah, so I think confidential VMs, well, a
Or I
confidential
guess
VM or a confidential container, but in that respect, it's still a virtual machine. I think the impetus really, the driver really is to be able to get access to a larger, lower security environment. So the way in which I would be thinking about this is I encrypt my data, I measure the entropy on a data set to make sure that it appears to be encrypted. It ships across the environment. That might be that might be a relatively manual process, so that I can put that data set into an environment where there might be multiple people around which might be accessing it. Now, in my context here, typically that environment, it's not a completely untrusted environment. It's not like going from a secure data center to putting it on a public S3 bucket. But it's definitely where you might want a lack of prying eyes accessing the data set and be able to tightly control it. So that kind of workflow where it's I bundle something up, I ship it across the boundary, I can work on it to provide a bit more access to more compute. I think the reason why I mention that is it's very similar to how you might operate if I was a machine learning engineer in a bank, which is I'd have to justify to someone on how I would collect information to then go and do some machine learning, even if it's relatively straightforward, regression machine learning. And the benefit from this kind of approach is consolidation, because now the compute facility is shared, whereas in the bank and in many organizations, otherwise the compute facility is fragmented, and that kind of moves more towards a multi-tenancy use case, which is I can have different compartments, I can have different high trust anchors. In this one, it's more of a generic one, which is I need to get access to something which is lower security, and otherwise it'd be completely prohibited.
Okay, and then the generalization is that the demand for confidential computing is for that low side implementation. You're not seeing it in the high side.
I think the high side implementation would be a different use case, which we can actually just jump to right now, which is, I'll jump into that as I walk through. So if you hold that thought for a second.
No problem.
When I look generically at many government environments today, so I'm not picking a particular country, I could pick most countries. I think the only caveat I would say from an Asia Pacific perspective is there isn't the high side cloud penetration that you would have in the US. So in the US, there's Azure government and AWS government and everyone government that isn't generally available in a lot of other countries. The market sizes aren't big enough. So typically, there's a risk-based assessment that they're making, which is I have some high security workloads on premise. I'm probably using a hyperscaler or a local cloud provider to do modernized low security workloads which are outside the fence. What the question is, how do I build this enclave in the private in a public cloud environment where I can tie all the information together? Now, this is definitely one of the use cases which I've seen significant interest on because people want to be able to push the workload out, but they don't necessarily have the ability to quantify or to build around their security controls. And the reason why I particularly wanted to focus on this one for a second is this is where the evidence and impact of confidential computing is really clear, like in terms of the memory isolation. The question is more, how do I chain everything together? So in this case, if I don't trust the network fabric, I have to bootstrap up a network security fabric on top. And that means I also need, from a CVM use case, to go through a set of chaining that I want to do. So that would mean, if I think about our Linux stack, I would want to enforce that SE Linux was on and it was not violatable, I would want to embed the network security policies in a context that that users couldn't manipulate it. So I have some hard verification that when I bring up an environment, the network policies that sit around it mean that you get some security sitting around that boundary, which is very hard to violate from inside the OS. So I think this one's not just about how the TEEs are used. It's definitely about how we surround the TEEs with sets of technology to manage, the encryption in transit as well, and that network fabric, because that secured pipe really becomes a hard thing to execute on, because you need to be able to progressively escalate privileges effectively. So say the environment has come up, how do I then give you some encryption keys to then establish an IPsec connection? Or as an example, if we want to pick a traditional protocol, it's one of the areas where some of the more modern VPN technologies, so some of the mesh VPN technologies become very interesting all of a sudden, because then you have a fabric which you can deal with in here. And that kind of leads me to answer the question that Dan, you really had, which is where do we see the use case in the high security workloads? And the guaranteed one that we have is to be able to build a platform experience where you have a decreased trust in the platform team. So if you think about the higher security environments, I mean, it's no surprise here, the higher security environments, you see not just air gaps which exist between organizations, but air gaps which exist within organizations, and that obviously drives a huge capital overhead for some of these teams. Now, some of them are logical, which will never go away around business continuity, but when we look at the core data center, the challenge is basically consolidation of risk. That all of a sudden the risk profile is going up for the environment. So that means the platform team, securing the platform team, making sure what they do, the amount of effort that you need to put into that gets to the point where you can't increase the size of the platform and achieve those kind of scaling benefits. So the goal there really is to say, can we use, if we pick, it doesn't really matter whether you pick CVMs or confidential containers or different form factor, is can our remote attestation for those workloads be the piece which is distributed? Because if we think about an attestation server, like something like Trustee or whether it's Keylime, the infrastructure required to run that is very, very, very light. And this leads to interesting questions around whether you can use that to do things like chained attestation. So can I have an attestation server which is passing trust off? Because I might, as a remote team, want to be able to have something which is effectively in a closet or held semi-offline to boot an attestation server which is living inside the platform, which the rest of my workloads can use, because that way I don't have to run my attestation server all the time. So I think there's definitely a discussion on chaining attestation. Or the other way I would also think about this is, in some environments, how do multiple parties that participate in the attestation environment, the remote attestation server. So it might be that you have a default position for the platform, which is run by the platform owners to increase the security profile, but then teams can optionally override that as well. I think the other one in this context is probably, there's probably a few workloads which are high risk would have to be interconnected, even if we don't have that full-blown mesh fabric. There's already workloads, there's always workloads that organizations are putting on the internet or putting onto the public cloud effectively because they're forced to, because there's no other financially viable way, but they might want to protect. So an example would be a KMS is the obvious one here. So if it's something like Vault, I think there's a strong desire to use some confidential computing around that. Does that answer your question, Dan?
Yes,
Cool.
thank you.
Great. Yeah. Okay, great. The other one where we're seeing quite a bit of interest is what do we do with edge devices which are have more limited compute and storage. There's some obvious ones that people would think about edge devices where you don't want to lose the IP, whether that's something which is flying or going under the sea. It's also ones where you want to have strong guarantees around the continuity of operations. So whether that's a camera, it might be a remote 5G site where you don't want to lose, you want to put some guarantees around the execution of the platform and the communication channel associated with it. This one becomes really interesting as it applies to some of the attestation use cases and bootstrapping, because you start to get into this, I would say, concern, like you have to, it's how do you trade off the security that you might achieve from remote attestation versus, say, a measured boot and self-attestation tied into a TPM rate, like something which is being put into the TPM, because there's a balance between I want to ensure that no one can touch this versus I want to ensure that it hasn't been manipulated. The postures are different, and no one can get access to the data. Has a much higher probability of having disruptions to operations if you lose the network fabric. So the further we get out to the edge, we start to see different concerns that people have in terms of, do they want to go all the way to confidential computing? Can they, depending on the form factor, do they have enough room to have a virtual machine interface in there to start the TEE and to have the infrastructure around it? Or is that just going too far for them, and what they really need is a measured boot and the ability to encrypt data at rest and do something a little bit simpler. So I think that sometimes it's really revealing just a few questions that they have and something that they need to explore further.
So, Chris,
Okay.
to that point,
Yeah.
if I may, and I think this is one of the things that hopefully we're going to see more of, is people realizing that you need to use the tools you have that are available and build systems which make the most of all the different pieces together, and that confidential computing is just one of the perimeters that you use, and that's kind of how it all sits together, rather than saying everything needs to be at the same level, because that's clearly not the case.
Yeah. I mean, absolutely. And like, if I just think about some of the one discussions I had this week, which was just around a robotic system, what they really wanted was to have, say, FS Verity on their partitions to make sure that no one could mess with the source code. Like, it was a much simpler use case. They didn't need confidential computing in that context. They really just wanted to have the integrity verification being really high, and then use that to layer in some technologies. Now, there's some associated technologies where you could see that they might want to protect some pieces with IMA, if they were, some of the really critical pieces. But it's really trading off that usability space. And I think there's a lot of experimentation that's really happening right now from people who have that room to think about what they're doing. So some of the research labs around this space are definitely thinking about it. I think the one I would kind of highlight there is I spent quite a bit of time with a telecommunications provider, and we ran through remote attestation, and the next question was where, and who, because they had a service provider interface. They wanted to build an overlay on a hyperscaler, which was sovereign. But it's like, do they own it? Does their tenant own it? What are the SLAs that they can achieve? That trade-off is where I think a lot of the discussions, the maturity is we're starting to get to. So I know that we want to keep it probably just about half an hour. So what I want to do is kind of jump into a climate deployment example. So we had a partner in this, which is a company called Ripple. Well, a company which many people know, called Ripple. What you don't know is they don't just have cryptocurrency. They provide a software platform which banks and other providers can use to implement cryptocurrency exchanges and trading platforms. Now, the problem with the cryptocurrency exchanging cryptocurrency trading platforms is they need to hold cryptocurrency. Even if they're never actually exchanging it out to the end client, if it's just a speculation platform, they still need to have that in reserve, particularly from a banking perspective. They can't kind of just speculate on it. So they have to have this reserve in there. And we're working with a Red Hat banking client for this, who's had significant regulatory pressure on them around their core operations because of the very public failures, I would say. And they've got a mix of on-premise and hyperscaler deployments. They're one of our large partners. They've got significant experience with Kubernetes. But this project had been running for a number of years, but had been running on some very bespoke security appliances. So the way in which I would really describe this is, I said the last scenario was really protecting critical assets. And obviously the piece of software which is signing the cryptocurrency transaction when the cold vault has in excess of $100 million in it is the critical asset, as are the keys which interact with the HSM. So in this case, they are still using HSMs behind the scenes to anchor the trust for the platform. There's two layers of HSMs which are involved. The easiest way to think about this is one is transfer out, one is transfer intra-bank, which is this thing called notary. And the real goal here was to standardize the architecture, to leverage the fact that confidential computing can provide, can allow them to use a platform which they've got experience with and have experience monitoring and securing in general. So in that case, for us, it was, OpenShift, the Kubernetes platform, and to use that consistency as a driver rather than hiding some hardware in a corner which they had no access to. Because the hardware in the corner, of course, leads to other kinds of attacks and leads to risk. And I would, it's very good I don't have the name on there, because horrifyingly, effectively their system integrity monitoring was someone walking into the data center every week and checking the lights were all green. Which is not where you really want to be with a really high value asset behind there. The idea here is all of a sudden now we've got a platform. Now the idea is to use confidential computing rather than just physical isolation. And we understand that they were using, I believe it was AMD Sev before, but not Sev SMP in this context. They weren't able to. They were using some degree of memory protection, but we weren't sure how much. But it was effectively a sealed bespoke security appliance that they had, so it was very limited room for them to maneuver. So the resulting architecture was real. I won't really go into this much detail, but to suffice to say that what we basically did was use the fact that Kubernetes now has some really nice network segmentation features on the software side, like Multis, the ability to kind of hook up into their network in multiple ways, where effectively the confidential container is brokering access between various components, and we try and isolate the workload as much as we can with the software constructs as well. The one thing that I would say is our experience with this, with the upstream, particularly those who are working on the upstream projects, is that the immediate shock that we got was there was a few enterprise requirements which were pretty big gaps. So dealing with the fact that this environment was not fully air-gapped, but pretty air-gapped. Like everything was mirrored down for us in terms of proxies. Dealing with non-standard CAs, like being able to manipulate the CA chain, was something which had to be kind of, I would say, manually injected into the code. Like we were lucky. There was a great deal of uncertainty as to whether we'd be able to use this the bank CA provider, like internal CA, based on where we were, and it was only we were lucky because it was only in the code base for a couple of months, and not something that people had really thought about. The other one I would say that was really the greatest challenge to this was explaining the remote add station, and I'll kind of circle back on this again. Building that external dependency tree and understanding why you need a remote add station. I think now that this is in production and there's a progressive security uplift as you build the platform and refinement in terms of what they're doing, they're starting to understand that a lot of the security controls that people want in these environments, like how do I enforce that only certain images can be pulled into the platform? Well, the only way I can do that is by first making sure my policy is right, and then ensuring that the policy is correct. Which is, we inject with the init data, so it's part of the attestation, ensuring that the data is correct through remote attestation. So those second order concerns it took a long time to come, and I think the way in which I would say this, it was really pushed by an application team, because effectively, to our advantage, Ripple had insisted on using confidential environments. They previously used the IBM mainframe hypertext environments in other clients. That push was really where which drove it, but the security team needed to come along for the ride a little bit more. So the other one I would say is for those of you who have worked with confidential containers before, storage is not our friend today. It's not a simple experience, and I would say the promise of some of these tools that we're introducing is that we try to make it relatively seamless in terms of the operational run, and attestation is where a lot of the extra work is. At the storage layer with confidential containers, which I know is a CNCF project, not a CCC project, but it is where there's a few missing gaps because no one really wants to manually format devices and then encrypt them within the pod, because that means that you're really injecting the confidential computing requirements in the way of the application. We do fantastic jobs getting secrets into the container, so they look the same as if it's in a normal container, but just the storage paradigms are just not quite there yet. And I would say if you wanted to build those overlay networks, they're not there yet either. I kind of mentioned that. The other one that I would say is that this is more of a personal one, is one of the areas where I think there's a bit of a challenge with some of this is effectively codifying some of the architectures. So from a trustee and COCO perspective, having those design patterns really, really baked, which are secure by default to give people the starting point, I think is where we're kind of, where I think a lot of people are struggling, having the kind of, that architecture framework in there as well. The other one I would say is that the networking side, if you're trusting your network fabric, it's all okay. Just deliver an MTLS key in to secure your connectivity. If you're not trusting your network fabric and you need to establish a VPN tunnel, the support around the ecosystem is not quite there yet. But that was just a quick run through at quite a late hour. But happy to take any questions. I'm just going to jump off the slides because I saw a few things pop up in chat.
I've got a couple of quick ones, if I may. Not questions, really requests. Yeah, firstly, fantastic. The first request is let's get some of the stuff out there. We need these discussions to happen and to be at conferences and on webinars and all those sorts of things. Let's find out a way to do this. This is absolutely exactly what the industry needs. Which leads me to the second thing. You said, let's get these patterns out there. How can we leverage the work you've done to maybe publish some of these things? CCC looks like a great place to do that, where everyone can collaborate on them in an industry-safe way and get some of this stuff out. I'd love to see this stuff out in white papers or reference architectures, something like that. So yes, please, and a huge thank you for all of this. It's absolutely fantastic.
Yeah. Thanks, Mark. I really appreciate that. But yeah, I'm more than happy to jump in. Yash and Roman and I will be seeing how we can make sure we can get as much of this possible out there as well. And the other one, of course, for the work that we're doing, I'm trying to make sure as much of it's upstream ready as well, so we can use it in multiple environments to make sure that the community it's accessible to the community as well.
Brilliant. Anything else before we let them go to bed? Because Chris, you need to be in bed, I think. Thanks so much for staying up. Really appreciate it.
Yeah, indeed. Thank you so much for that. This is a great talk, Chris. If people want to ask questions outside of this meeting, are you part of the TAC mail list?
I'm not. I will get myself onto it at some stage as soon as I can. I'm sure Yash can. We'll make sure that happens.
You can reach out to me as well, and I can relay them to Chris.
Fantastic. Thanks, Yash.
Great work by Red Hat. Great work in APAC as well. It's really good to see this stuff.
Yeah.
And some of the differences you mentioned are really important to understand, not just for APAC, but also for sort of the EU and stuff like that too. Thank you.
Thank you.
All right, fantastic. Thanks again, Chris. Boy, again, jam-packed schedule today. So one good topic after another. I think it was a year ago that we added Manatee to our portfolio of projects. And so we're going to get an update from the Manatee project. And I know that
share screen.
Yeah.
Yeah. Okay. Let me get started. So, this is the first time of Manatee for the annual review in CCC. I think the project was donated last year around the end of the year, so it's almost more than half a year. So there are some progress, and I will touch a little bit on the technical updates and some of the outreach activities we made in the past few months. So to recap, Manatee is an open source, trusted research environment project for secure and verifiable data analytics. It leverages privacy-enhancing technologies like confidential computing and differential privacy to protect sensitive data while maintaining usability. So since joined CCC last year, November 2024, there's no change in technical charter, and there was no budget allocation relevant to Manatee, and there's no outstanding license issue until now. And we haven't studied the open SSF best practice for this project. I think we can start working in the following year to have that badge and show in the showcase, show in the README. And the project contact changed to me, and for the technical updates, we did our first community release, and we also have a new AI related use case, and we did some code refactoring, polishing, and added a new TDX T backend, some document, and the homepage launched. And also
Ming Shen, are you showing more slides? We're only seeing the title slide at the moment. I'm not sure if that's intentional.
That's weird. Oh yeah, I'm sharing more slides. How about now?
Yeah.
That's good.
Yeah, go back. This is what is Manatee, and I'm here in project progress. And for technical part, we updates community. We have community release with code refactoring, documentation, and we have one AI use case and support new PDX backend. And we also did several outreach activities to promote this project in different events. So for technical highlights, I will go very, very like briefly, and you can check it out in the repository. Uh, the first thing we did after the donation is to have a community release to do some file restructured to make it more open source friendly, and we did code refactoring and reconstruct the building system to use Bazel. And also we did CI integration with GitHub Actions, and also the documentation to make it more user friendly. And to better support local testing environment without TE, we integrate with Minikube, so you can launch locally in Mac. And also we launched a homepage, have all the details of like getting started with the first example and some tutorials and our new features use case. And also we add a new backend TDX. Originally, I think the first version is using AMD SEV, and then we added TDX. And the last highlight is new use case for verifiable AI model evaluation. Um, uh, the first use case for Manatee is always data sharing for research. And then we found that recently model fairness evaluation is becoming important, and providing more trustworthiness and verifiability in model evaluation is very important. And sometimes private model evaluation could be an issue if you want to share to a third-party tester. So that's why we introduced this new use case to demonstrate how to use Amenity for model evaluation. Okay, I'll just dive into this one. I think this is one of the highlight. And from verifiable evaluation of AI models, what we want to address is how to improve the trustworthiness of the model testing process, including like fairness evaluation, bias evaluation, and trust and safety property evaluation, so on and so forth. And also, we want to the Manatee project want to ensure the integrity and confidentiality of public and private models in testing. And because of the feature of hardware attestation report, the output of Manatee evaluation process contains the evaluation result as well as a verifiable attestation report to make sure the integrity of the result is verifiable. And that's the overall idea of this use case. And we have working demo in the repository as well as a tutorial to launch this demo. I think we have a recording of this demo as well, but I will check offline to make sure you can just play with this new feature. Okay. And also we did several outreach activities in different regions for STEM in Belgium and Confidential Computing Summit San Francisco and Singapore Asia Tech. And we also plan to attend the AI Info Summit in the coming months. I think with CCC's booth, we plan to demo the AI model evaluation in the booth, so people coming with the AI background know the value proposition of confidential computing. And the next step for this project, we still continue want to improving the AI model evaluation workflow. Currently, the workflow will be like customized, and there are already some standardization to make it more formalized, like the AI model card, like can show the evaluation result, and then we can improve the trustworthiness with attestation. And things like C2PA also comes with those features. And this is the first thing. And second thing, we also want to explore new use cases in trusted research environments. Now we have one from us, and also the AI is like a new innovative use case. But there's a lot of traditional data sharing for research use case we want to reach and explore. Then integrate with the new T backends and cloud provider. That's the thing. We really want to bring the GPU T capability in this platform because currently, if you look at the demo is currently executed in CPU environment and the report as well. So, but some of the evaluation can only be done with GPU. So that's something we want to integrate. And we have heard like requirements from some other potential use case needs other cloud providers. Currently, I think only Google Cloud is supported in Manatee, but we will explore other cloud providers can be integrated in this platform. And the last one is, of course, a security best practice badge. Yeah, I think that's pretty much about the overview of this next 7, 8 months of Manatee project in CCC. I'll take
That's
any
a
question.
yeah, that's a great update, Ming-Shen. It's an exciting project, and it's nice to see it's continuing to grow in features. I guess maybe I would let you ask a question of us first. So the OpenSSF best practices badge, is that a clear process for you?
Yeah, I think so. Well, we haven't started looking at it. I think all the process requirements and integration. I think the document is well documented, so we can if we have time to start with that. I think there's no issue with that.
Okay, great. I think you'll find as you start going through it that maybe 80% of it is just checking boxes that you're using modern frameworks like GitHub, and that provides the kind of transparency that that badge is looking for. I see Mike's hand is up.
Yeah, you know me, always have questions. So firstly, I'd say also look at the OpenSSF baseline as well. That I think is useful. One question was, how many contributors do you have, and across how many companies? That's always organizations. That's always an interesting thing to understand.
Yeah, I think we internally we have several contributors here and there, even cross teams. Externally, I have seen one or two, but not that far. So that's something we want to work on.
So again, if there's something we can do at the CCC to help with that, to sort of raise visibility or encourage people, we're always interested in those sorts of things. So please let us know about that.
Yeah, of course.
Sorry, Karen.
I heard like the mentorship program can also help that. But I haven't seen a lot of successful story like in CCC. Oh, I have seen one blog post. Sure, we will definitely leverage those benefits.
Sure. And the last question was, you said that you're now supporting TDX. Is that equal support with AMD SEV, or if you just doing one of them now, you prioritizing one over the other?
Yeah, you can choose one of the SEV and the TDX.
Equal support. Okay, brilliant. That's fantastic. Thank you.
Okay, well, I will build on one of Mike's questions here, but I encourage the other TAC members to take a look at the annual review process link that I dropped in a chat and make sure that we've got everything covered to everybody's satisfaction. But Ming-Shen, if you think about the kind of capabilities that you want to be providing with this project, who are the ideal consumers of that? And maybe that can help us recruit on your behalf for those users to come in and start trying out the project and then maybe eventually becoming contributors.
Yeah, I think because the value of this project is data sharing for research or trusted research environment. I think the first customer should come from the academic community who want to use or share data with other organizations. We actually we reached out some of the organizations making standard of academic data sharing or trusted research environment. Especially in European countries, they have a community to to make this like interoperability across different organizations. So that's the our main target, and I have seen some of the feedback from them. I think I also started use that, and also we also discussed with since I was in Singapore in Asia Tech, I have seen some GovTech people who are also interested in to share like public data in the target domain in a secure way. So they are also interested in this project as well. So that's the potential customer reach out to us, or we have the discussion before. But for AI use cases, we do have this need. I mean, TikTok also want to explore the application, and also in the AI Infra Summit, I probably will talk with other people to see other AI related company have this needs to do the model evaluation.
Okay, great. And am I remembering correctly as well that ad tech is one of the potential use cases for this?
Yeah, ad tech, of course. But ad tech a little bit difficult to jump in because they are existing workflow. So we haven't go into that community to talk about this project for now.
Okay. Any other questions from the audience?
I've had some very good talks today, I have to say. Really, pretty fantastic. Thank you very much indeed to everybody.
Yes. Okay. Well, I guess maybe one just last thought for you, Ming-Shen. In our list of update stuff is also about license scans. I don't think anybody gets real excited about license scans, but as you move to more commercial adoption in the future, it's nice to know that you've got a clean bill of health from a licensing perspective. So there's tools out there that will be available for your project when that becomes more relevant to you.
Okay.
All right. Well, I think that brings us to the end of our agenda for today. Next time, I think the main topic that we have on the list is the funding proposal that Ming-Shen started for the academic research that we touched on during the announcements. And that is currently the only thing that I see on our tentative agenda for next meeting, which would be August 21st.
Hey,
If people have exciting, yeah, Ming-Shen.
Regarding this funding program, have we talked about this in tech? I remember we discussed in the governing board meeting, but not in tech. Probably we
That
need
might be worth doing as
context.
well.
Yeah.
Yeah, that would be good to get more of an introduction to it for the rest of the TAC here. Mostly we've just mentioned it in the announcements from today. So
yeah, the next time.
Yeah.
I will also follow up with Chris and get more details on the storage requirements. I think that is something that as the CCC, we can, like you said, ratified or defined that could make adoption easier going forward. So I'll gather more requirements and I'll follow up and we'll go through his experiences one-on-one.
That's really good. If we can start a track on that, that might make a lot of sense. Cool.
All right. Well, thanks for everybody's engagement today. A lot of good topics, a lot of good things covered,
Thanks,
and stay engaged on the mail list. And until the